Hello, everyone, and welcome. My name is Katherine Hambleton. I'm with NASA's Office of Communication. Thank you for joining us today at Kennedy Space Center here in Florida to talk about the science that will be launching to the International Space Station. Dragon is just about packed and ready to launch atop of Falcon 9 tomorrow at 5:55 p.m. in the evening. We will have time for a few questions as I bring each of our speakers up today. For those on the phone, you'll press *1 to be entered into the queue. And for those online, please use the hashtag AskNASA. So here with me first, I will have Dr. Camille Aline with the Program Science Office of the International Space Station Program, and Ken Shields from the Center for the Advancement of Science in Space, otherwise known as CASIS, the organization that manages the National Lab. All right. Camille and Ken, would you like to join us?
Yes.
And Camille's going to give us an overview of what's happening in the world of science on station. And Ken is going to tell us a little bit about what's going on with CASIS.
Thank you, Catherine. Welcome, everybody. We're so excited to have you guys here today, and we're really looking forward to the launch tomorrow. The CRS-11 will launch over 4,500 pounds of research supplies and science investigations, including about 2,000 pounds of unpressurized cargo, 3 science instruments that will be flying in the trunk of Dragon. You'll hear a little bit about that in a few minutes. It also has the capability to return samples for us and return payloads, and it will, in about 30 days, will be returning about 1,500 pounds of that science experiments. All this research is supporting over 220 investigations currently going on during increment 51, 52 on board the space station. And these experiments really support a number of disciplines, scientific disciplines, including biology and biotechnology. You'd hear about that in the rodent research and fruit fly investigations. We also have the capability to do physical sciences research in the area of combustion, complex fluids, and also material research. We have experiments supporting the earth sciences and space science. We also have some investigations that are developing technologies and advancing those for future space exploration. And then we have a suite of science education experiments and activities from students not just across the US, but across the world, who will be flying things like CUBE satellites, a constellation of CUBE satellites from 6 developing countries. So to date, we have had over 2,000 investigations that have been conducted on board the space station, and about 2,000 researchers, scientists, and students who have done research from 93 countries around the world. We use the space station to advance our scientific knowledge that has a benefit to improving the quality of our lives here on Earth. We also use it as a technology test bed and to do research on the human physiology to further our space exploration goals. We are also using it to develop a marketplace in low Earth orbit for commercial companies. And finally, it is really a great test bed for a blueprint for international cooperation so that we know how to work and live with other countries as we further our exploration goals. So with that, I will turn it over to Ken, who will talk to you a little bit about the U.S. National Lab that's managed by the Center for the Advancement of Science in Space.
That's great, Camille, and thank you. And you could hear from Camille's briefing all the great things that we're doing on Space Station through NASA and the International Partnership. I'm from CASIS, the Center for the Advancement of Science in Space, and we are the nonprofit, non-governmental organization that manages the U.S. National Laboratory on board station. Now, what does that mean exactly? Well, we are the sponsor or the gateway or the front door for non-NASA related uses. So our mission is not to necessarily fly things on the space station to further our exploration objectives or to go to the moon or to visit an asteroid, but we're trying to sponsor research on station that will have a direct benefit to life here on Earth. Now, this launch, SpaceX 11, terrific launch. I think it represents another awesome example of the progression of the ISS and the National Lab as a wonderful platform for not only commercial innovation, but also innovation from a number of different users. We've got users on board this flight that represent other government agencies, academia, and quite a few in the area of STEM education. representing every science discipline that you can think of. Camille touched on several, some very exciting payloads in the trunk in particular. We're all looking forward to those. But also, we've got payloads from companies like Procter & Gamble. Matthew Lynch from Procter & Gamble is conducting a colloids experiment in microgravity with the aims of developing improved formulations for dozens of consumer products that we all utilize every day in our life. Another great example is from Dr. Su from UCLA, who is looking at improving a drug design or drug development that will repair bone or even prevent future bone loss. Once again, great effect for an improvement for life here on Earth. And lastly, we have an investigator, Dr. Kovalevsky from Oak Ridge National Laboratory, who is doing a protein crystallization experiment aimed at increasing his understanding of an enzyme that is associated with the antidotes that we design and build to fight venom and chemicals that attack our nervous system. Once again, very important and effective impact for life here on Earth. All of these are great examples of the utility and the importance of the space station. We've got a video that we'd like to show you right now to tell you a little bit more about the Oak Ridge National Laboratory experiment.
Hundreds of thousands of people die in the world every year from organophosphate poisoning. Crystals are a symmetric collection of molecules. So every next molecule in the crystal sits in exactly the same orientation and in the correct symmetry. It's ordered. By growing crystals on the space station, we hope to grow better, more uniform crystals that we cannot grow on Earth. Once we get protein structure, we can design better, faster acting antidotes that can be used against pesticide and nerve agent poisoning. It's very exciting to send my research to space. We should keep pushing the frontiers of science.
So yeah, just to wrap that up, as you could see, very important work here. And I think it's a great example of how the ISS can really represent, it's part research park, part business incubator, part laboratory in space that can serve a broad spectrum of interests and users. It is of extreme value to us here in the United States, and I think it underscores the importance of what we're looking to do next with future commercial space stations and how we're going to continue to develop this economy in low Earth orbit that Camille alluded to. And that's all. Look forward to questions later on. Thank you.
We'll take questions from folks here in the room. If there's any questions about the general science that Ken and Camille have talked about before we get into our additional speakers.
The crystals, they said that it was going to be used to protect against pesticides and other chemicals. What does he mean by that? Is it going to be in some sort of filter system or the spacesuit? What exactly are they going to be doing?
What Dr. Kovalevsky is really looking at is he's looking at the proteins that actually are the construct or the basis of the enzyme that's associated with the antidotes that we designed to fight some of these toxins that might attack our nervous system. So from an experimental standpoint, it is a very basic research experiment. He's going to grow these crystals in space because in space, we have a very quiescent environment. We don't have a lot of surface tension. It's just a very, very nice place to grow very large and well-defined crystals. Those will be brought to the ground, taken to Oak Ridge National Laboratory for neutron diffraction, and then they're going to use the geometry. They're going to try to solve some geometry to better design more effective antidotes.
So like a serum that would go into your arm?
It could be a serum. Yes, it could be a serum. It could be a pill. I'm not sure what the delivery mechanism is, but it's the basic building block for what that antidote is, what that drug is.
We've got a question back here.
So I see that there are a lot of private companies that are putting in investments for experiments they'd like to have carried out on the space station. I was wondering if there's a lot of companies expressing interest in that right now, or is it more of a novice thing that these companies that were mentioned there are groundbreaking and there's more to follow?
There are a number of companies. There will be more to follow. To say there's a lot, that's very subjective. I can tell you when we started back in 2012 and we assumed managing the lab with increment 37, there weren't a lot of people with awareness, particularly in the private sector, of what the opportunities were to use the International Space Station. That's what we've been doing now for the past several years, and we can see a very steady progression and a serious ramp up from the commercial sector. And what's important, and I think what's very interesting, not only from a user or demand side, but also from the supply side, we're seeing a lot of companies wanting to put commercial facilities on station to host experiments. You're going to see a presentation by one of the companies later today.
Got another question over here.
It was mentioned that there are several schools from around the world that are sending up research. I just wanted to know more about the process that led to your decisions about, which ones went up and what some of those experiments might be, if you guys are aware.
So the space station is an international partnership, right, between the US, Japan, Canada, Russia, and Europe. And so each of those partners have their own national goals, and they select the research to support those national goals. So the CUBE satellites I talked about is being led by JAXA, and they have a program called the BIRDS Project that they are collaborating with in developing countries to help developing countries get access to space by developing CUBE satellites. From the US perspective, we have a bunch of sponsors that actually select their own research. CASIS is one of those for the US National Lab. Across NASA, we also have like the Science Mission Directorate and the Space, Life, and Physical Science Office, and then the Space Technology Mission Directorate that actually select their research in those areas to fly. So that's how it's prioritized.
The other countries that are sending CubeSats up tomorrow?
Oh, so this project is a collaboration between students from Japan, Nigeria, Ghana, Mongolia, Bangladesh, and Thailand. So it's six developing countries flying 5 CUBE satellites. You're welcome.
Got one question in the back here.
So you mentioned that the ISS is the private contractors and such are ramping up, and they want to put experiments onto the space station. How do we see that moving if it's ramping up? Is that going to increase the life of the station? Because as of now, there's only so many years left. So let's hope that it stays like as a viable option. Is that something that this helps with, kind of keeping the station alive longer?
That's a great question. I think it does, but I'm probably not the best equipped to answer that question, and I'm biased. I think we need it until 2050, but that's probably not a reality. I definitely think that this space station, this International Space Station, is laying the groundwork and the foundation for the space stations that will come after it. It's my own opinion that, yes, we're seeing a very nice progression of demand and utility and usefulness that I think will, in fact, bring about other space stations. Camille may have further comments.
Yeah, so we have appropriated use of the space station to 2024. That's what Congress said. There's life in the space station through 2028. And one of the things I mentioned is the expansion of this commercial marketplace in low Earth orbit, so that once the space station, the end of life comes, there will be a commercial presence that NASA could actually, or the US could buy services, just like we're doing with SpaceX or Orbital, buy services in low Earth orbit to further our research so that we can focus on going to other destinations beyond LEO.
It will be a sad and joyous moment when this one goes away. Right?
Absolutely.
Thank you very much. Oh, we've got one more question over here.
Hey, let's get to the party favor. So Rosa, a lot of excitement, I think, in the solar array industry on that. You've got the old traditional kind in the background up there. So with this Megaflex, granted, it's not going to be actually used in generating solar power on this mission. It's just going to be, I think, just to see how it works and develops. But what is potentially groundbreaking about this new Megaflex solar array.
Well,
So-
hold that question because we do have the Rosa PI that will be making a presentation, so you will get everything
Never mind.
about that.
All right. Thank you, Camille and
Thank you,
Ken.
Catherine.
Thank you.
Next, I'd like to welcome Dr. Keith Gendreau and Dr. Jason Mitchell. They're going to tell us about some hardware going up in the trunk of Dragon that will look at the physics of the densest objects in the universe and may pave the way for a future GPS-like system for deep space.
Hi, can I have the wide shot? So NICER stands for the Neutron Star Interior Composition Explorer. It's a mission of opportunity that was selected as part of NASA's Science Mission Directorate Explorer program. It's going to be the first space mission that's dedicated to the study of neutron stars, which are really fantastic objects that were discovered 50 years ago this fall. A neutron star starts its life as a star like our sun, but maybe 10 to 20 times bigger. And it burns through its nuclear fuel. When it finishes burning its nuclear fuel, the star explodes in a supernova explosion. The core of that original star collapses into a small, dense object that's about the size of a city. So if you could please show the neutron star video. This object is about the size of a city, maybe 20 kilometers across, yet it contains the mass of up to 2 suns. It is the densest matter that we know in the universe, and if that original star was a little bit more massive, then the result of that supernova explosion would have been the production of a black hole. Now, what NICER is going to do, among many things, one of the more important science objectives of NICER is to measure accurately, 5% accuracy, the radius of a neutron star. This is an order of magnitude improvement compared to our state-of-the-art knowledge right now. And we're going to be doing this through a number of techniques, but one of the more interesting techniques that we're going to be using is light curve modeling. So in light curve modeling, what we depend on is Einstein's theory of general relativity. And Einstein's theory of general relativity says a lot of things that are really unusual to our regular life here. One of the things that it talks about is how matter affects the local space-time around it, and that rays of light will actually deflect a little bit as they're felt by the gravity pull of the matter. And for the matter that we're used to here on the Earth, which is very low density, we don't really see light bending. But if you take something like a neutron star, where the densities are really huge, you imagine something like Mount Everest squeezed into a sugar cube, then the gravitational light bending is a very strong effect. And so if you could bring up the hotspot video, please, I'll give you an idea of how we're going to use this. So in this video, you see 2 stars that have the same mass and radius. In the star to the left, you see a hot spot that's rotating in and out of our field of view. When the hot spot is near us, it's bright. And so when it goes around to the other side, it disappears. And so the pulse goes from a very high brightness to 0 brightness. The image to the right, we've actually turned on strong gravity bending. And what that allows you to do is look at the far side of the neutron star. So as that spot goes around, you actually see light coming from the backside of the neutron star. This affects our light curves so that you get a very subtle but measurable change in the shape of the light curve. And so in order to do this, to make this measurement, we have to make an instrument which has enough sensitivity to give us high statistics of the shape of this light curve. And so Jason Mitchell is going to show you a little model of our instrument right now. It's in a stowed configuration like you see. This dimension here is about 1.2 meters. We have some launch locks that are there to allow us to survive the launch on the Falcon 9 rocket and go all the way to the space station. When we get to the space station, we're going to be robotically installed and put onto the top of space station at ELC, Express Logistics Carrier Site 2. At that point, we're going to release our launch locks, and the instrument will unfold, giving us eventually a view of the sky. So if I can have the turntable video come up, please. What you see in this turntable video is that we have an additional 2-axis gimbal that allows the major instrument to have a very clear view of the sky. The major part of this instrument is this big box structure. It's got a collection of X-ray telescopes. This is one of these X-ray telescopes. This is made at Goddard Space Flight Center. We have 56 X-ray telescopes in there. We chose that number because it's the maximum number we could fit in there. And some of the objects that we're trying to do science with are relatively faint. Not all of them are like this, but we want to get as much signal as possible. So each one of these X-ray optics concentrates light onto a dedicated detector at the other end of the box. The Massachusetts Institute of Technology has built a really amazing instrument that makes use of commercial, off-the-shelf silicon drift detectors from Amtech. This instrument has a capability, this detector system has a capability of detecting individual X-ray photons that are concentrated by our mirrors down onto the detectors, individual X-ray photons, and for every photon, we measure the energy of that photon to 2%. We measure the arrival time of that photon to better than 100 nanoseconds compared to a GPS time standard. And we can do this throughout our mission. So over an 18-month mission, we can time coherently add photons collected at the beginning to the end to make these very statistically significant light curves that will allow us to do the light curve modeling, among other things. Now, this system has to point very well because to collect our signal, we have to look at the stars. So as the space station goes around the Earth, it's constantly tumbling to maintain a zenith direction and a nadir direction for Earth science and space science. So we have to compensate for that. So we built, I think, perhaps the most sophisticated pointing system for astrophysics on space station. This box weighs about 400 pounds, and we're going to point this at the arc minute level as these stars rise. And to do this, we have an international team that's helped us build this. So we start with the Denmark Technical University, DTU, provided a star tracker to us, which tells us where the instrument is looking at any time. That data is sent to flight software made by Goddard Space Flight Center, running on a computer made by Moog, a big producer of spaceflight hardware. This flight software instructs our gimbals to actually adjust their position so that we can keep lock at the arc minute level on these stars. Every ISS orbit, about 90-ish minutes, we're going to be looking at between 2 and 4 objects, and we're going to do this nearly continuously through our 18-month mission on space station, hopefully longer. We worked very closely with the International Space Station Program Office. We had tremendous support from Johnson Space Flight Center, Marshall Space Flight Center, folks here at Kennedy to design an instrument that makes full use of the resources available to do our science. We're getting the most science we can get thanks to the help from these folks. This instrument that we've produced has order of magnitude improvements in energy resolution, time resolution, and sensitivity compared to the last major X-ray timing mission that's flown, which produced nearly 3,000 peer-reviewed papers in its life. So I'm expecting this to be a major paper producer of science on the International Space Station. And we have a team of scientists from a number of universities, NASA field centers, national labs across the country and the world that are working to make this possible. Now, the other partnership that's particularly exciting about NICER is it's a partnership between the Science Mission Directorate at NASA headquarters and the Space Technology Mission Directorate at headquarters. We're going to look at a subset of pulsars in the sky called millisecond pulsars. These millisecond pulsars, some of these millisecond pulsars, the pulses that we see are so regular, they remind us of atomic clocks. The ticks come extremely regularly. And you find atomic clocks as the basis of the global positioning system, which allows you to navigate to this place using your GPS receiver. The cool thing about this technology demo that we're going to try to do with NICER is that neutron stars are distributed around the galaxy. And so we can actually build a system that will allow us to navigate from low Earth orbit into the solar system and beyond. And this is Jason Mitchell, who is the lead for the pulsar navigation, and he's going to tell you a little bit of that experiment.
Thank you, Keith. Could I have the navigation video? So the name of the technology demonstration that will be part of NICER is called Sextant, Station Explorer for X-ray Timing and Navigation Technology. So I think you'll see that pulsars from their initial discovery were immediately recognized for their utility in navigation. If you're familiar with the plaques that accompanied the Pioneer and Voyager missions, you'll know that there's a graphic there indicating the location of Earth with respect to pulsars distributed throughout the galaxy. And so our ultimate goal with Sextant is, I'm glad Keith defined GPS, so I can just use the acronym. Everyone's familiar with GPS, but our goal is to turn the G in GPS into galactic, make it a galactic positioning system. The initial steps with this technology demonstration for Sextant is on ISS using NICER's real-time science feed on board with the software augmentation to try and maintain, using only those observations, the position knowledge of NICER to better than 10 kilometers. That's a small step in proving compared to GPS, but it's a giant step for using only pulsar measurements. And that will help us get into deep space and possibly even into the deeper solar system. The partnership between the Space Technology Mission Directorate and the Science Mission Directorate has allowed us to participate in a science-tuned instrument. So the scalar design that Keith mentioned for these 56 individual telescopes, this is perfect for us because the ISS environment is challenging from a navigation perspective because ISS is moving around very fast. So we would like, from a deep space navigation perspective, to stare at these pulsars for a very long time to maintain very, very good accuracy. For deep space, potentially we'd like to see hundreds of meters of accuracy over the long run. So this science-tuned instrument allows us to think about shrinking down to a more realistic size instrument where instead of 56 detectors for this large collecting area for us to be successful in the ISS orbit, we can scale down to 1, 2, 3 and see the performance. And I think to kind of wrap it up and stay on schedule, the scaling and the partnerships, especially specifically for ISS, gives us the ability to do cutting-edge science and develop the techniques for navigation that will carry us perhaps out of the solar system. With that, I'll open it up for...
All right, so let's take some questions here in the room. Again, for those on the phone, you can press *1 and use the hashtag online, Ask NASA. We've got a question right over here.
So I'm very interested in the navigation aspects. In the future, when you've refined everything, would this be something where the ship that was navigating would be communicating back to an array like this, or would they be carrying something on their ship that was a descendant of this and using the pulsars directly for navigation? I realize this is way out in the science fiction world, but I'm curious what you're thinking.
Ultimately, the goal would be for this to be something that would be carried with the vehicle, with the vessel, so that you can think about it as being able to maintain your navigation solution autonomously, independent of any communication. But of course, you would be communicating back to some location that you would hopefully have a well-surveyed location. You don't want to be off on your own for too long. But yes, it would be autonomous navigation on board.
Other questions? Got one right here. Just a second, we'll bring a mic over to you.
I actually have two questions. The first would be, for the navigation, would it be using a triangulation system to measure angles between two pulsars?
It would be more like trilateration. You would think about, as Keith pointed out, these light curves. We're looking to reconstruct those pulses. And we have models. So we look at those models about where we think the pulse should have been when we construct it compared to what we actually constructed. So that kind of becomes a line of sight measurement.
Okay.
Did it arrive a little early or a little late? And then that's what we use to form the fundamental measurement to take the navigation. And that's the challenge, because then that processing is serial. Because you look for a long time at a pulsar, get a measurement, then you look at another pulsar and get a measurement.
Okay. The second question was, when we're talking about like long exposures, I'm picturing it almost, like a camera being pointed at a pulsar. How long is an exposure that we're taking for one pulsar?
So on any given orbit of the ISS, we have maybe a couple thousand seconds that we can look at any particular object because the Earth gets in the way. But like I said, every photon is time tagged absolutely, and so that we can build up a lot of little exposures to have the megasecond exposures that we need to do our science.
And we've got one right over here behind you.
Are you guys working with commercial partners on this? I mean, is there any tech transfer capability so that once the lab has had its use for it in space, people could use this technology here and on Earth?
So there have been a number of companies that have helped develop some of this technology over time, and there is a commercial interest in making this available. Our interest is in building an instrument to do the science and demonstrate the capability and then pass it on for commercialization.
All right, thank you very much. Also heading up in the unpressurized trunk of Dragon with NICER is a project to test a concept for solar arrays that unroll like a tape measure. And here to tell us a bit more about that is Dr. Jeremy Bannock.
Thank you. Get my hardware set up here. So the goal of ROSA is to unfurl for the first time in space a new solar panel technology. And while at the same time understanding better how this new deployment technology works in the space environment. So the primary technology that we're demonstrating on orbit is what's called high strain composite mechanisms. This is an example of one of the full-scale tubes, the full-scale structure that's used to deploy the wing or unfurl the wing. And I will demonstrate it for you here. So as you begin to unfurl the tube, it naturally wants to unroll, but yet it's compact when it's stowed, which is the nature of the high strain, is that it can be stowed to a compact package for launch. So I'll start here. On orbit, we would deploy much slower than that. Deployment takes about 4 minutes on orbit. So there are several different science objectives we hope to achieve. One of them is that we want to better understand this deployment behavior. One of them is actually retraction, so you get a sense for how that works. So we want to better understand the deployment behavior, and the reason for this is large structures like this one cannot really be tested on the ground. They collapse under their own weight. They're designed for space loads and not ground-based loads. So engineers get around this today by adding some additional reinforcements to the structure, but that always creates questions of whether this thing will actually deploy reliably once you get on orbit and you remove these additional supports. So that's the reason why we really need the microgravity environment of space. And it's the microgravity combined with the extreme temperature environment that we really need. We really need space station. We really need on-orbit flight to test and demonstrate. So that's a full-scale tube there. This is a 1/10 scale model of the wing, and it gives you a better sense. I'll deploy it for you here. So that's essentially the deployed wing on orbit. Ours will be 15 feet long by 5.5 feet wide. So deployment is one of the science objectives. One of the other science objectives is to measure and understand the structural dynamics of this wing. So when a satellite maneuvers on orbit, it stresses whatever long structure is attached to it. That could be a solar array, it could be a reflector antenna, it could be a radar antenna, it could be a long instrument boom. It stresses that array, and that long structure responds by vibrating. I don't know if you could see that. But we really want to precisely characterize that vibration signature of this solar array wing. It's a characteristic of the stiffness and mass of the structure. And the reason is because satellite designers or guidance, navigation, and control experts, they really need to understand those vibration signatures so they don't lose control of their spacecraft. So they have to precisely predict it. So we are gathering data on the structural dynamics to refine our prediction models to help implement ROSA in the future. So that's the second science objective. The third one is we want to better understand how the wing behaves when it transitions from full shadow to full sunlight. So a structure like this that's so thin, I mean these composites are only a few millimeters thick, this blanket material is only a few millimeters thick, that means it heats up really fast when it moves from shadow to sunlight. And that rapid heat up in a matter of dozens of degrees in a matter of a few seconds can again cause the wing to shudder a bit. It's what we call a thermal snap. If ROSA happens to be attached to a telescope like Hubble, well, we don't want to bump the camera, we'll just put it that way. So we want to make sure that there is no thermal snap behavior on ROSA. But ROSA is primarily a power generating array. So we also want to measure the power production performance of this wing. And we're only populating it with about 10% fill factor of cells, which is about 300 watts. A full array of this size would be about 3 kilowatts of power. So we just want to make sure that those cells have survived launch, which can be on the order of 50 times greater than the accelerations on Earth. Pretty violent. So that's our science objectives. As far as the on-orbit operations go, we will be removed from the Dragon trunk approximately 9 days after docking. After being removed, the ground-based robotic arm operators will position ROSA away from station. We will command deployment after having checked out our initial flight computers. Like I said, deployment will take about 4 minutes. During deployment, station cameras will be watching the wing. We'll be looking for any unexpected movements and motions. We expect it to be a smooth, linear, slow deployment, but we'll be watching with station cameras anyway. So after deployment, we will begin our dynamics experiments, and those dynamics experiments will be actuated by oscillating the base of the ROSA payload. So if you could bring up the stowed wing view. So there we go. So at the base of that wing is a motor that oscillates the base back and forth at a specific frequency. And what we're really doing is watching the tip of the wing moving back and forth as a response to that oscillation at the base. And we'll be doing that with some accelerometers, but primarily with a technique that we call photogrammetry, which can move off of that image. We'll get to the deployment in just a minute. We have a deployment video for you. So this is a sample of the actual blanket. So you see it's an open weave mesh, and there's a Kapton joined to that mesh, and then these photovoltaic cells. In this case, they're aluminum mass simulators. But you see those white targets there. We're using those for a technique called photogrammetry, where at least 2 station cameras will be looking at the wing at all times during these dynamics experiments, and it'll be tracking the position of these targets. So with a triangulation technique, we can then back out later what the precise relative position of these targets is, and then reconstruct the vibration frequencies and amplitudes of the wing. So we'll be running those dynamics experiments in full sun and full shadow, and then during eclipse exit. And that's basically our operations. So why don't we go to the deployment video? Give you a real-time sense of how this wing deploys. So that's the actual speed there. We have some dampers that restrain the strain energy in those tubes a little bit. So in the center there is that photovoltaic blanket, and you start to see some of those mass simulators unrolling. Accelerated here. You see those white targets distributed on the blanket, those photogrammetry targets. And then near the end of deployment, the wing, I'll slow it down again here. And what you really see at the end is not much at all, which is a good thing. We want the wing to be nice and controlled, and we don't want any subtle dynamic motions near the end of deployment. So that's the ROSA experiment. I did want to mention just briefly a little bit about the applications. The fact that this is really is a multi-agency experiment. This wing has been developed by funding from NASA STMD, from the Air Force Space and Missile Systems Center, and of course AFRL, Air Force Research Lab, which is the primary sponsor. You know, the reason all those agencies are involved is because all satellites need power, all spacecraft need power. And the traditional method of generating power is solar panels that are constructed with these square plates that are accordion folded and joined with these mechanical hinges. But the problem is these traditional methods are bulky, and they tend to be heavy, and we just can't make them any bigger today than we just can't make them any bigger. That's what it comes down to. So ROSA solves this problem by reducing mass by 20% and reducing stowed volume by 400% over these traditional approaches. So there are some really cool applications. The commercial space industry, Space Systems Loral, for example, is considering ROSA for satellite TV, for satellite internet, and communications spacecraft. The Air Force is considering it to increase availability and access of GPS. And perhaps more exciting is the fact that ROSA enables scale up to much larger wings. So currently we're limited to about 15 kilowatts per wing. ROSA can scale up to 30, 100, or even 500 kilowatts per wing. And that opens up applications for things like solar electric propulsion. NASA's considering that for interplanetary missions. Certainly the Air Force is interested from a LEO to GEO transfer perspective. So there's some really cool applications for ROSA coming down the pike. But it's not just about solar arrays, actually. I mean, these high-strain composite materials are being considered for other deployable structures like reflector antennas and these radar antennas, solar sails even. So ROSA is a pretty cool technology that we're really excited about the potential applications coming down the pike.
And I believe you have an image to show where it is on station.
Yes, thank you. So this is a position of ROSA on station. And if we go to the next image, you can see two of the cameras that are pointing at the wing. So this is for the deployment and for the photogrammetry data measurements that I mentioned. So we'll just be hanging out.
All right. And I know we have at least one question. Do you still have a question?
That was it.
Okay. You got it answered. All
Okay.
right. We've got one question over here.
So I'm curious, since obviously you only have the smaller models here, with the one that's actually going to be going to the space station, what is the width of the wing when it's fully rolled out?
5.5 feet.
That's the
width is 5.5 feet.
Oh, I guess I meant to say the thickness of the wing.
So the blanket itself, this is representative here. It's really only just a few millimeters thick.
Even on the space station
On station,
one, it's going to...
yes, that's right. It's a flexible blanket that has to be stiffened by tension mechanics, which is why you need the booms.
Thank you.
All right. Another one right there.
So that's a beautiful design. I am curious because engineers always plan for things that fail, and part of what you're looking at is the things that can go wrong.
Mm-hmm.
What are the problems that you're kind of anticipating and bracing for?
It's a very good question. So I'm very careful to explain this as an experiment, not a demonstration. Those are very different. In an experiment, we anticipate the unanticipatable. So we instrument the heck out of the thing so that we can capture any behavior that we may not even expect. So the dynamics is a big question mark. How does the fundamental frequency change when we move from testing on the ground to testing on orbit? And even testing in full sun versus full shadow, where is that center frequency going to be? And it's going to take some time for us to oscillate the wing at just the right frequency so that we can excite it and capture that frequency and that dynamics behavior. So that's probably one of the biggest uncertainties now that we really hope to learn.
Thank you.
All right. We've got one up here.
So you had mentioned that this new design is able to do it longer and larger, and you said that the old traditional wasn't able to do that. What makes it so different? Is it just the size of the vehicle? And if it is, why not just make the vehicle bigger so you can fit more and more solar panels?
Sure. So there's two issues, mass and volume. Volume is the bigger limiter here. And if you notice, the stowed form factor of this is short, but it is long. With a rigid panel array, they're long and wide, and they're also thick. So you're really limited by the surface area of the bus that you're mounting it to, and you can only stack so many panels up before you run into the volume limitations of your launch vehicle fairing. And you know, even adding additional wings on either side, there's been demonstrated challenges on-orbit challenges with trying to deploy the wing in a complex way using these simple mechanisms. One final point to answer your question, with these materials, they're so much different than traditional mechanisms in that they have some flexibility to them when they're deploying. You know, they have some give to them. So that makes them much more amenable to much larger deployments because you don't have the risk of binding hundreds of different hinges together because each hinge now has a little bit of compliance to it, a little bit of flexibility.
Do we have other questions here in the room? Again, if you are following online and have questions, please use the hashtag AskNASA. We do have a question over here.
The as far as power production of this design, the increase in size, and the big scale picture of human space exploration in the future, what does that translate into as far as what we may be able to accomplish that we can't accomplish now? And how did you guys come up with the description party favor?
Party favor is a great one. The other one we've used is a paper towel roll with 2 tape measures on either side. So it's whatever your analogy is. So the space exploration question is one I'm not real qualified to answer since I represent the Air Force, not NASA. But what I would say is solar electric propulsion is a great source of propulsion because it requires so little fuel. So you can travel much longer distances with, as long as your wing is large enough, you can generate enough power. So that's, I think, one of the simple answers to why it's a useful technology for interplanetary type missions.
All right, thank you very much. A third payload going up in the unpressurized trunk of Dragon is a project that will enable new capabilities for Earth imaging, and it also is sponsored by the National Lab. Paul Galloway is here to tell us more about that.
Good afternoon, everyone. I'm Paul Galloway. I'm with a company called Teledyne Brown Engineering, Huntsville, Alabama. We've been building space hardware and operating payloads for almost 50 years for NASA and solving complex problems for both NASA and the Department of Defense. I'm very excited today to tell you about a payload that our business decided to take a risk on and go out there and extend ourselves, go a little bit further than we've ever gone before. And that payload is called the Multi-User System for Earth Sensing. So today what I'm going to tell you about is I'm going to describe what is MUSES. I'm going to talk about the commercial aspect of MUSES, since that's important to us as a company. I'm going to briefly describe the MUSES objectives and then possibly talk about some advantages of ISS. If I could have the first photo, please. That's the MUSES platform. It's a gimbal system. It has very precise motors for pointing. It has star trackers. It has accommodations for up to 4 instruments. Some of those, what you see on the pointing platform there are some those conical shaped objects, and then the smaller triangular or recessed pyramids. Those are our basically our course and fine alignment for installing payloads. In the middle of that, you see a position for a mounting stud, and that's the attach point for the payload. There's also with the yellow covers there, those are the blind mate data and power connectors for our instruments that will be installed on MUSES, and I'll show a picture of that a little bit later of actual instrument installed. So we have 4 positions, 2 large and 2 small. MUSES has the ability to point and track. We can basically look forward, also go over that target, and then look backwards. We also can skew port and starboard. So it gives us a lot of versatilities in these types of instruments that want to go up and view a single point on multiple locations. The space environment is very harsh. As you know, the vibration environment is very severe for SpaceX. So our payloads, our instruments are sensitive, have a lot of mirrors and small, minute mechanisms, sensitive optics that have to be finely calibrated on the ground. So it's very difficult for us to launch our instruments in the trunk of MUSES. So one of the great resources that station provides is these repeated flights. And these repeated flights allows us to launch our multiple instruments over time. It also allows us to give a soft ride to these instruments. We can pack these instruments in foam, and the G environment that they see for launch is around 3 Gs packed in foam versus about 20 Gs for just hardware that's basically fixed in the trunk. So it's a very big advantage for the instruments that are flying on Muses. The commercial aspect of Muses is very important. It's a private-public partnership that was developed under a cooperative agreement with NASA, and so it's some shared risk between NASA and our company. So there's some first about Muses being a commercial payload. It's the first multi-user facility for the ISS, specifically for the ELCs, the Express Logistics Carriers on ISS. So what Muses will do is actually have a multiplier effect. We take one payload site on ISS and now provide 4 payload sites. So it greatly increases the payload utilization of ISS for payloads that are in the range of 50 to 200 pounds. Next image, please. Okay. The left side of that image shows our 4 payload accommodation sites. What we do is we provide some very generic resources for these payloads, things that you would use in your home or office almost. We have 28-volt power for the electrical power for these instruments. And then we also provide Ethernet communications, gigabit Ethernet communications for high-speed data communication. So by simplifying these interfaces for these payloads, we've greatly reduced the number of interface requirements that payloads have to meet to get on ISS. We've reduced the barrier for entry for small companies that want to build payloads to fly on ISS. And this would essentially allow a small country to have their own space program. They could build an instrument, put it on Muses, and start a space program at a very low cost by comparison to a dedicated flight on a small rocket. So it's very interesting. On the right side of that image, we have a star tracker and we have an inertial measurement unit. Those allow us to determine the rotational rate of our pointing platform. We're also a very early user of the external wireless communications on ISS, maybe the 3rd user. It's a new capability on ISS. As you know, when you generate video or images on your home computer, you quickly fill up your hard drive. So this is a very data-intensive experiment, these imagers that go on the Muses. So we had to tap into multiple data sources on ISS. We use every possible data link or communications link on ISS to get our imagery down. We use the low rate, the medium rate, and the high rate. And this wireless system also enhances our ability to get the imagery off our platform, get it transferred over to a server that we have in the U.S. laboratory in an express rack, commonly used. Next image. All right, let's talk about our first instrument. 2 years, well, not 2 years, but 2 flights from now on SpaceX 13, we'll be launching an instrument called the DESIS. It's a hyperspectral imager. It detects in the range of 400 to 1,000 nanometer. It's a visible and near infrared system. What we do is we take that 400, that range, and we slice that into 2.5 nanometer sections. So what you end is basically for each image on the ground, you end up with a very large cube of data at very fine spectral ranges. So as you can see, telescopes and optical instruments can be quite long. We can't fit these kind of instruments into the trunk. They exceed the volume required, and also we talked about the vibration environment is severe. So even for an instrument like this, it's 36 inches long, you still have to fold the optics in there to get the resolution you want on the ground. This detector will detect at 30 meters or 100 meters on the ground. And if you were to turn on that instrument through that 6-inch aperture there, if you turn your instrument on, let it image over, say, 20 seconds, it basically paints a 100-foot wide strip on the ground. And then you have a very long exposure time for this maybe 30-second exposure. And that allows you to quickly image the entire Earth's surface, take these images, characterize them, catalog them, and make this imagery available to not only commercial customers but also science organizations. Our objectives for our flight is, of course, the successful robotic installation on ELC-4. It's paramount. We also have to make sure that our gimbal systems are working accurately and that we're getting the precision pointing that we want. So before we even unlock our launch locks that you talked about earlier, we will move the gimbal to make sure we're getting good feedback from the gimbal system before we ever unlock it. And then the robotic arm will come back over, unlock 2 launch locks, and then we'll articulate our gimbal the full range of motion, which would be 25 degrees fore and aft, 5 to starboard, and 45 to port. We also want to verify these communications links that I talked about to make sure that we're getting our data through the ISS to the server and then to the ground. That's a very important part of our initial operations. Another objective is just to get this thing launched. I'll be honest with you. When you spend 5 years of every waking moment thinking about something, you're just glad to see it finished. And we want to get this thing launched. We need SpaceX to have a successful launch. And we also need our robotic operators to delicately remove Muses from the trunk and move it over to ELC4 and install it. And then we're going to turn it on, and we're going to be open for business on ISS. Thank you.
All right. Do we have questions here in the room? We've got one over here.
So you talked about the potential mapping capabilities of this technology. Do you have plans in place with this current launch to do any mapping of the Earth's surface, or is this just testing the technology more and trying to get it into place?
It's there's no instruments for ground detection on the initial launch of Muses, so it's really just testing the technology, the data transfer, the precision pointing system.
In the future, do you see this being used to map the Earth's surface in some way?
Oh, absolutely. The ISS passes over 90% of the Earth's inhabited surface, so that's a great advantage of the ISS. Plus, we have a low orbit. So the purpose is to completely map the Earth's surface over time and put these large amounts of data into an archive and make it available not only to academic, industry, and government customers, but also we have our part of our charter is to provide data to a program called SEVERE. It's for disaster response throughout the developing world, and we will, anytime an incident would occur on the Earth, we could take that imagery and make it available to people that are in disaster response business. It's just one of many sources of data that's used for responding to disasters on Earth. So it has a very, very useful applications for our Earth.
Thank you.
So you said that you've spent 5 years of every waking moment. How many man hours actually went into that? Because I know you're not the only person who worked on it.
No, not at all. But it was done with a very small team. Part of the commercial approach is doing a lot with a small team. So we had a team of about 10 engineers working over a 5-year period. You know, some coming and going depending on their expertise, but average 10 people. But I can't say enough about the assistance that NASA provided. We could not have done this without NASA. They gave us the launch. They've given us countless amount of hardware that we need to do the testing, our access to test facilities. So it was truly a partnership between NASA and the small company that I work for.
Thank you.
Do we have other questions? We have one back here.
So since this platform is meant to give other companies kind of a way to get up there in countries and things, what's the functional lifetime of something like this? How long can it stay up there, and can it be reused if something, can you retire an instrument and put a new one on, and how long does that last?
Well, we designed it for a 5-year life, but we fully expect, based on the hardware that we've installed on here and the testing we went through, we fully expect to last the life of Space Station. So we will be there as long as station's there and as long as we're operating. And
thank you.
All right, thank you very much. Another investigation heading to the National Lab will use rodents as model organisms to help shed light on osteoporosis. Dr. Chia Su is here to tell us a bit more about that investigation.
Good afternoon. Hello, everybody. So I'm gonna talk about Rodent Research 5, which is systemic therapy of NEL1 for spaceflight-induced osteoporosis, or in short, we're gonna try to grow bone in space. And so I'll run briefly why it's important to grow bone and a little bit about the molecule NEL1, and then I'll briefly describe our mission. And so why is it important to grow bone? Well, if you think about it, everybody has bone, and you have cells in your body that make bone, and you have cells in your body that destroy bone. And if you have an imbalance of the two, you get overall bone destruction and loss of bone mass or bone mineral density, and then you can get osteoporosis and osteoporotic fractures, which is a huge problem on Earth and potentially even bigger problem in microgravity conditions. Just on Earth alone, past the age of 50, 1 out of every 2 to 3 women is going to develop an osteoporotic fracture. And 1 out of every 4 to 5 men will develop an osteoporotic fracture. So it's a huge, huge issue. And on average, after age 50 on Earth, you tend to lose about 0.5% of your bone mass per year. So 0.5% per year. But in space, in microgravity conditions, the astronauts can lose up to 1 to 2%, or on average 1.5% per month. So you can imagine the implications for long-term space travel, our mission to Mars. So for humans to be in microgravity conditions for prolonged periods, we have to have a way to prevent development of osteoporosis and a way to treat that when they come back to Earth, or if they land on a planet with gravity, we cannot have our astronauts sustaining a mission debilitating fracture. So some of the things that we've been working on at UCLA is where NEL1 was discovered. So this is our team. It was discovered by Dr. Kang Ting, looking at craniosynostosis patients. So this is a condition where in little babies, they're born with bone in their skull that formed there prematurely. So probably those of you who've held a baby, you know the head feels kind of soft. And that's because the bone plates haven't fused yet to give the brain room to grow. So certain babies are born with those bone plates fused in a condition called craniosynostosis. And that's also in and of itself a big problem because the brain does not have enough room to grow. So what Dr. Ting at the time at UCLA was trying to answer the question, what was causing this bone to form during development? And so the answer was NEL1. So there was too much NEL1 there. And so this is about 20 years ago. And so since then, we've been saying, well, how do we harness NEL1 and get it to form bone where we want it to? So that was how we started. And with the help of Dr. Ben Wu at UCLA, he engineered now the NEL1 to make it last longer and also a much more targeted delivery to bone for this experiment on the ISS. And then we also have Dr. Jenny Kwok, who is our project manager for this. And then so I'll go over a little bit about our experiment. Next slide. So we are going to be sending off 40 rodents to the space station. And there's going to be 40 ground control on Kennedy Space Center. And before launch, they're going to undergo a bone scan. You can see in the green arrows. And after launch, then when they're in position, we're going to start NEL1 therapy, and the astronauts will be administering NEL1 to the animals on the International Space Station, and then we'll have the same thing in the ground control here. And then so overall, the animals are supposed to receive 4 doses of the drug every 2 weeks. And one of the interesting things that we're going to be doing is after 2 treatments, half of the animals from the International Space Station will be coming back to Earth for live return. So this will be the first ever American live return. And so that will allow us to address some very critical issues. That is, these animals have been in the microgravity environment now for approximately 4 weeks. When they come back to Earth and we continue treating with NEL1, how well do they respond? And that will have implications for humans who may be in microgravity conditions and develop osteoporosis. How will they potentially respond to NEL1 therapy when they're back on Earth? And so, and then overall, then the same thing, exact treatment will happen to all the Kennedy Space Station animals, except they will be a 3-day lag. So what that means is then we will know everything that happened on the ISS, so then we can replicate those conditions as much as we can on Earth. Next slide. And this is a rodent research hardware system developed by NASA Ames that really makes all this work possible. So there's a transporter unit that is for launch, and then an animal access unit so that we can get the astronauts can get to the animals, and then also a habitat unit for the animals to stay in the space station. And after this, I'm just going to show a brief video of some of our studies. Thank you. Next slide. And so overall, that just ran through our studies, and just some disclosures. I'm a founder of a company called Bone Biologics that is working on developing NEL1 into a human therapeutic. Next slide. And I want to thank everybody for your attention. This is a picture of our mission patch, and all of this work would not have been possible without support, of course, from CASIS, as well as BioServe and Taconic, who supplied the animals, and SpaceX, and also, very importantly, the National Institute of Health, especially NIAMS, National Institute of Arthritis and Musculoskeletal and Skin Diseases, as well as National Institute of Dental and Craniofacial Research, who funded a lot of the background work to make NEL1 work possible. Thank you.
Thank you. Let's take some questions for Dr. Sue. We've got one up here.
Okay. Admittedly, I do not know a whole lot about rodent psychology, but them floating and being in microgravity for the 2 weeks or however long they're up there, wouldn't that, since they don't understand what's happening, would that stress on their bodies, that physical and possibly mental stress, like I said, I don't know, possibly alter the way that the experiment goes, since that will be something they are definitively experiencing differently than the ones on Earth? Also, they're taking 2 flights while alive, and you never know how that impacts them and the way that they think, because we know that with people, at least, stress can negatively impact your body.
Yes, that's an excellent question, and I think a lot of the groundbreaking work in making this possible is really the work by NASA Ames, who developed the whole rodent research habitat system, and they've been tested on previous missions, so we're R5, and so it's really a way to have the animals stay healthy, happy, engaged, and so even on this round, when all of this is very carefully approved by animal research welfare and all of that, and we were including things for animal enrichment, and the NASA Ames people even had pictures from earlier flights with some of the animals, and they seem to, at least the younger ones, really enjoy being in microgravity. They're floating around, spinning in their cages. And so there really has been a lot of work out from the NASA Ames crew in terms of how do the animals stay fed, how do they stay, relatively clean, where did all the poop and things go, and do they have, and yeah, there's things in the cage they can climb on, and so they have day and night cycles, so all of that has been worked out very well, and so our mission would not be possible without all that work that they did and all the previous test flights before to evaluate the system.
We have one up here. Just a second. We've got a mic coming to you.
Can you explain the mechanism of NEL1, please?
Definitely. So it is an extracellular a secreted molecule that is secreted in the extracellular space, meaning outside of cells. And so it floats around, and then specific cells that have a specific receptor for NEL1, NEL1 can then bind to those cells with the receptor and activate all the signaling inside that tells the cell that they need to grow bone.
Is that being used here on Earth right now?
It's just
For
experimentally.
osteoporosis?
No, it is still it's only in preclinical studies.
Okay.
So
And what's your
all
timeline for getting it into clinical trials?
Usually for a typical drug, it's anywhere, on average at least 10 years.
Thank you.
For developing it as a drug, it's still in the initial stages. We're still in preclinical, so a lot of it for developing into a drug involves the human study. So I would say we're probably very early on.
All right, we've got one question over here.
How do you translate the results from the rodents into the humans?
So excellent question. And so rodents were really selected by NASA as a model organism, and I'm sure there's other people here who can answer this even better than I can, that is because they model so many things that humans experience. So a lot of the genes we have are modeled on the rodents. And so they're really one of the best models, and they're small. So that they make it feasible to perform these studies on the International Space Stations. But rodents model many human conditions very, very well.
All right, over here.
What is the method for giving the mice the treatment of NEL1? Is it like an injection? Is it oral? And then do you know which astronaut's going to be doing that administration?
I believe that they've already trained that we don't. I don't recall the exact. I think it might be Pamela, but Peggy. Yes, I believe so. And so that's where also the NASA Ames crew have been training and all of that. And it would be intraperitoneal.
Did I see another hand somewhere? All right, thank you very much. We actually do have another model organism going up to station on Dragon. We have fruit flies that are going to help us learn more about mechanisms in the human heart. Here to tell us more about that is Dr. Karen Okor.
Thank you. Hello, everyone. The goal of the research that my colleagues and I do at SBP Medical Discovery Institute is to understand heart function in both health and disease. And the goal of the work we're doing in collaboration with NASA is to extend that work to understand the role of microgravity in cardiac function. The reason we look at heart function is, of course, it's very important to your ability to live, but it's also the most common cause of death, heart disease, in the industrialized world. And there's also a number of dysfunction parameters that have been documented in astronauts. And so we would like to understand the role of microgravity on astronaut heart function in order to try to prevent long-term effects when they are in space for long periods and after they come back. But there are real-world implications as well. For people who are spending long periods of time in bed rest or immobilized, we expect that what we find in our studies on the ISS will have implications for maintaining cardiac function under those sorts of situations. So we have developed at our institute a number of ways to look at heart function in the fruit fly, and we will be using those to try to understand what happens with respect to long microgravity exposures when these flies come back. So they will be going up to the ISS for approximately half of their lifespan and coming back, where we will then bring them into the lab and perform a number of assays on them. So I'm sure you're all asking yourselves, why on earth would we like to look at fruit flies as a model system? Well, one of the reasons is because fruit flies share about 75% of disease-causing genes with humans. So we have a very nice genetic model in the fruit fly system. My colleague Rolf Bodmer also discovered one of the first heart developmental genes in the fruit fly. He called it Tin Man because when that gene is mutated, there is no heart formed. But it's been subsequently found to be very important in human heart development. So there are very great similarities between the way the heart is formed in fruit flies and in humans. Now, the heart has a different structure in fruit flies. It's a linear tube, but I'm sure you probably didn't know your heart starts out as a linear tube and only twists later in development to form the heart that you're familiar with. And so we have a lot of similarities in terms of genetic basis. It turns out that there's a lot of functional similarities. The rodent heart beats about 10 times faster than the human heart, and the fruit fly heart beats about the same as a human heart. And that means that many of the important functional proteins in the fly are more similar to the ones in our heart than in a rodent heart. The other reason to do this is, as was just mentioned, they're small. In fact, they're smaller than mice. We will be sending up approximately 90 vials like this. And if you'll roll the video, you can see a close-up of what I'm showing you here. This is a vial with food in the bottom, and in the video you can see there's quite a few fruit flies climbing around. This is essentially a self-contained unit that can house thousands of flies. In fact, we'll be sending up approximately 4,000 to 6,000 eggs that will hatch on the ISS, and when they come back, we'll be able to analyze their heart function, having spent half their life in microgravity. This is showing you our lab, and this is how we analyze heart function. We take movies of the heart beating, and we can then, using a computer program that we've developed, analyze in great detail the function of these heart cells. And in addition to function, we can then, from the same flies, stain them and look at the morphology of the heart so we can see how microgravity affects the contractile elements within the heart muscle cells. We can also then do genetic analyses on these hearts. We've done what's called RNA-seq analysis on as few as 4 to 6 hearts. And I hope you can imagine how small an amount of tissue that might be. We can analyze these hearts through dissection, but when we try to do biochemistry on them, size matters. But we can, with the thousands of flies that we're going to get back, we'll be able to pool this tissue to varying degrees and do more extensive biochemical analyses once they return. Now, our experiment will take roughly 90 of those vials and we'll put them into 6 boxes that look like this. These boxes were developed in collaboration with our colleagues at NASA Ames, and they have a little viewing window, so it's possible to see what's going on inside. What you can see right now is just the food, but that will slowly get eaten by the larvae, who eventually will eclose from pupa on the sides of those vials and become adults. And it's those adults that we're interested in initially when they come back to see what happened to their hearts. But we're also interested in something called epigenetics. What happens to the babies that those adults produce? So once they come back, we'll let them have offspring, and we will raise those to approximately the same age as the parents that we analyzed. And we will then analyze their heart function to see if there are lasting effects in subsequent generations from prolonged microgravity exposure. Obviously, these are all important questions that most astronauts would like to know, but it's also important to understand if there are environmental kinds of influences that can affect function in offspring. And so these are the sorts of things that, in more general basic science terms, are significant for people on the ground to understand. And so these are the sorts of things we hope to address with this mission. We have already sent up on SpaceX 3 a test of this system. We sent up one box. We did get live flies back, and some of the things we learned from that mission, we are going to be continuing to test on this mission. So we expect quite a bit of genetic and functional information when we're done with these studies. And I think that's all. Thank you.
We'll take some questions here in the room. We've got one over here.
What is the lifespan of a fruit fly, and what % do you expect in 6 months to lose?
So they'll only actually be up there for 1 month. Their lifespan is 2 months. And so 1 week of a fruit fly life is about a decade in human life terms. So they will, the eggs that we send up will hatch. They'll come back after about, as an adult, about 3 weeks. So they'll be roughly 30, 35 years old, and so middle-aged. We're also sending up adults who will have babies on the ISS, so they'll be a little bit younger, but we won't have them quite so precisely aged. So it turns out aging, just like in humans, has an effect on the heart and the fruit fly. And the heart function gets worse as they get older. So we want to get them reasonably young so that we can separate the aging effects from the microgravity effects. Yes.
So I know that a lot of times when you send stuff up into space, you get results back that are exactly the opposite of what you were anticipating, like with the recent telomere studies. What in the previous experiment were you surprised by, and you're double checking this time?
Yeah, so there were some structural changes in the heart that we hadn't anticipated. We expected that there would be different size hearts in these flies that came back, because that's been documented, some subtle changes in astronaut heart size. And we did see that, but then there's extracellular matrix kinds of changes that we didn't anticipate. And so we're testing exactly that on this flight. And there's a few genes that were misregulated that we're investigating further, so stay tuned.
All right, thank you very much. So future space explorers will not only need to combat the effects of microgravity, they will also need a robust life support system to sustain them on their journeys through space. With us now, we have Miriam Sanjasingh, and she's going to tell us about an investigation that may improve life support systems for future space exploration by looking at how liquid and gas behave in different shapes.
Can you go ahead and play the video?
This is how you're going to drink your coffee. Future space colonists will drink their coffee this way. They will make their toasts on New Year's this way. That is so cool. Good to the last drop.
You know, while it's fun to drink from a cup, these cups are actually a test bed for looking at ways to make fluids flow in this microgravity environment. Cheers.
Cheers.
And we can go ahead and put that image back on of the life support process. So capillary structures for exploration life support, which we call C-cells, is actually an X project that was granted by Johnson Space Center in 2016 with the goal of bringing a technology demonstration or experiment that was sponsored by a NASA agency to space station within 1 year. So we had a very quick turnaround. And I kind of jumped on this proposal. I think being able to take some concepts that seem simple enough to create a cup in space and really apply those to life support systems is very exciting to me. So what this does is it actually brings a very complicated problem, which is fluid management and microgravity, which we currently deal with using rotating systems and membranes, special coatings. those systems tend to fail one way or another eventually. And this is just due to either phase separation or old age wear. And so what these capillary structures do is essentially take that problem and make it very simple by simply relying on geometry. And that is something that Don Pettit was showing in his cup experiment. And so if we go back to that picture, what this is showing, kind of yesterday's coffee to tomorrow's coffee, we've got the waste collection system, which is collecting urine, and bringing it to a water processor. In this case, we're wanting to have a capillary evaporator. So what this evaporator does, and here's an example of one, is hold the pre-treated urine in a capillary structure and allow air to flow over the many surfaces that this structure would allow. And then what that does is it pulls the humidity from the urine, leaving the undesirables behind in the capillary structure. That air is then moved on to a condensing heat exchanger in the air revitalization system, and then it kind of takes a turn down into the water processor. So what the water processor does is then make drinkable water. And so from that, Kjell Lundgren was able to create his sort of Keurig space cup aspect and be able to really enjoy the smell and taste of freshly brewed coffee on the space station. Another thing that happens with the air, though, not to forget, is being able to scrub that air so that it can be reused over and over again. And so in this case, what this part here is a very fundamental demonstration unit of the fluid mechanics that would go into a carbon dioxide removal system, actually a regenerable one. So a liquid sorbent would be flown through a contactor, and that would then provide a very direct interface between that liquid sorbent and air. That sorbent would then pull out the CO2 from the air and pull it away, bringing it to another chamber where it would then be regenerated, pulling the CO2 off and sending it off to another system or dumping it, and then allowing that fluid to be continuously used to scrub carbon dioxide from the air. And so these systems are very simple. You pour it in, it's kind of like a bucket and sort of like a slick wall. In this case, you have a full regenerable system with only one pump. And basically, we're kind of like blowing the minds of our engineers back in, kind of JSC, KSC, Marshall, because we're not using the typical technologies to manage the fluids. These technologies only work in space, sort of, kind of, with some various tweaks. They can work on terrestrial grounds like Earth and on Mars. But these are specifically designed to work in microgravity with very minimal waste. So how do we get to Mars? We get smaller, lighter, and we become more reliable. This is how flat our water recovery system, for about 1/3 of a liter, would be going up and then being thrown away, as opposed to some of the larger processing units. So if we go on to the next slide. Again, these are just 2 portions of the entire experiment. The experiment actually has 6 different experiments included. 3 of them are focused on carbon dioxide removal. And so from left to right, the first one is actually a science article. This is going to allow Portland State University to really evaluate how fluids will flow into 4 parallel wedges, which are open to air and then recombine and be brought around. The next experiment, next 2 actually combined together, really demonstrate the carbon dioxide removal system. So the more complex is the 2 contactors being run in series. The item in the middle, bottom middle, is a simpler version that is intended to show that we can actually flow fluids of different viscosities and surface properties and really understand how they flow and be able to predict how they flow. Up on top are the ones that are more associated with the capillary evaporators. So the one in the middle you see right here, which is a demonstration unit of a capillary evaporator. We'll fill it with an ersatz and then use a fan to dry that out over 5 days and watch how it dries in its container. The first one is a science article. So what this is looking at various shapes to see how different dimensions like height, width, shape of the individual capillary pores will impact fluid stability and the evaporation rate. And then finally, on the very end is a foam infill demonstration. So this is a piece of foam that we're going to use to show that fluids will be actually able to wick into that foam structure and free up space for air to flow over the surface of that foam for evaporation process. We're going to have about 50 hours of crew time. This is a very crew-intensive experiment. We wanted them to have fun and really see the science that's happening with this experiment. And then out of that, we're going to get more than 500 hours of science out of this kit. And then one little thing to note, so again, we're trying to keep it simple. While the eventual technologies will be using some more complex fluids, we wanted the crew to be able to feel free to experiment, and so we're using our wonderful ersatz of Kool-Aid. Very easy to see, very nice to work with, and if there's any spill, they can kind of just suck it up. Any questions?
All right, thank you. Let's take some questions here in the room. Again, if we have folks on the phone, it's *1, and using the hashtag #AskNASA if you are online.
This Ask NASA question, if these systems are only really work in microgravity, how do you test them before you send them to space?
Very good question. So there are actually quite a few experiments that are happening in order to evaluate these systems. For the evaporator, we actually created some microgravity versions of these containers that have a bottom, and then we evaluate the surface evaporation from sort of the crenellated edges here. And then we also work with Portland State University that has a drop tower, so we get about 2 seconds of microgravity data, and we've been able to show on some of the subscale mock-ups of these different technologies how the containers fill, how they flow. For the capillary sorbent, there's actually a Space Act agreement that NASA has with Honda that's developing a very similar technology for their hybrid cars in order to clean their air and reduce their power draw on their batteries. So that's one application where we're actually using the very, very similar technology on the ground.
Thank you. Do we have other questions here in the room? Got one over here.
So you said that you get 500 hours of science out of that. I'm curious what exactly that entails, like research-wise.
So actually, the way that we're collecting data here is through video and still imagery, really time-lapse imagery. And so for each of the experiments for the carbon dioxide, this is very, very handsy. So we're collecting video imagery as the crew is performing the experiment. For the evaporation experiments, we have enough for 6, 7 different evaporation experiments, and each of those would happen between 3 to 5 days at a time, and we're going to be taking time-lapse photography over the entire evaporation process.
Thank you.
All right, any other questions here in the room? We've got one over here.
So when you were showing how small that collapsed, you said something about the throwing them away. Would these be reusable things, or would you send up multiple filters?
So that's actually something that we are currently evaluating. We're going to be doing the trade study. So the first pass, very, very simple, is that we would fill it once, let it dry, and then throw the residual contaminants away. Currently, we're working with the brine that's generated from the urine processor assembly, which is about 25% of the water that was in total collected from the urine and flush water. So it's kind of thick to begin with. However, if we were going to use a more dilute solution, we'd want to go ahead and reuse these. And so one of the kind of cool things is that once these get dirtied up, they actually wet a lot better. So we will probably be able to contain the fluids better, and hopefully we can maybe whisper to Peggy Whitson to try that up on the next increment.
Are there any other questions here in the room? Did I see another hand somewhere? All right. Thank you very much. So thank you all for joining us today. We'll be broadcasting the pre-launch news conference today at 4 p.m. to hear more about the mission launch operations. And then be sure to tune in tomorrow for live launch coverage starting at 5:15 p.m. You can visit nasa.gov/SpaceX for more information. And to follow along with our researchers and their investigations, you can visit nasa.gov/station.